Okay, so today we start with a new chapter. It's chapter 2, and it's about quantum computation. So quantum computation you can think of as being a topic that combines two disciplines, namely computer science and quantum mechanics, so to say. So physics from the quantum mechanical point of view and computer science. And it's, I mean, what you do there is you use the quantum mechanical description in order to perform tasks which are relevant for computer science. So usually you have a problem, you want to solve this problem. And in computer science, what you do is you write an algorithm with which you can solve this problem. And in quantum computation, what you do is you write also an algorithm, but for the algorithm you use now the properties of a quantum mechanical system in order to solve this problem. And what turned out is that if you do so, there are particular problems. Let me stress that I say there are particular problems for which it is known that if you use a description from a quantum mechanical point of view, then you can come up with algorithms to solve this, which work faster than any algorithm you can think of from a classical point of view. Classical meaning from a description on using classical physics, right? And this is what makes quantum computation so interesting, because we know that there are problems which can be solved faster on a quantum mechanical point of view. So we usually say with the quantum computer, right? And let me also say it again. Okay, these are only a few particular problems that we know. There's a whole set, but still there are particular problems. And now, in the forthcoming lectures, I'd now first like to start with defining what is now our information carrier. If we consider now, if we take the point of view and consider quantum mechanical systems as those systems which we use for our algorithms. So there, the classical counterpart of a bit is a qubit. Okay, so first we're going to define a qubit. Then we're going to discuss some operations of qubits. So how do we describe operations of qubits? And then we consider whole registers of qubits, so many qubits, and define operations there. We're going to see how these look like. And a very useful approach that is usually done is that once you know what your operations are, you're trying to decompose these operations into elementary sets. So we then see that any multi-qubit operation can be decomposed into an elementary finite set of single and two-qubit gate operations. That's what we're going to prove, that there is such a decomposition. However, what we're going to find out then in the end, that if you want to decompose an arbitrary multi-qubit operation into these finite sets of elementary gates, you see that if I increase the number of qubits, say I have n qubits, then we need an exponential number in n of elementary gates in order to perform such an arbitrary gate set. Okay? This tells us it's not so easy to find an algorithm based on quantum mechanics such that okay. So I'm going to say it again. So we're going to find out that if you want to decompose an arbitrary multi-qubit operation into a concatenation of your set of gate operations in which you can decompose every operation, then you need an exponential number of your gate from your set. Okay, this is a problem because meaning that you cannot decompose every multi-qubit operation efficiently, meaning that it's not straightforward with this decomposition to find an efficient algorithm based on quantum mechanics. And this means that if you have a problem and if you want to solve it on a quantum mechanical system with a quantum mechanical description, then you better come up with an interesting way how to solve it efficiently, right? And in the end, we will then gonna discuss a few such algorithms where we do find an efficient way how to implement those with quantum mechanics. And we're gonna compare them with the best known classical outcome, and we will see that there are such algorithms with which we can perform these tasks better than on any classical computer. Right? But I want you to know that it's not straightforward to do this, to find such algorithms. Okay, so the next point is that since quantum computation merges these two fields of computer science and a quantum mechanical description of nature, if you want to really understand quantum computation in detail, you should also try to approach this topic from a more computer science point of view. And this includes also what is called complexity theory. So if you want to understand quantum computation in detail, you must dig into complexity theory and try to understand, okay, what are all these complexity classes behind all these operations? How do they interrelate? And then try to understand this from a more from a complexity theory point of view. In this lecture, I'm not going into this direction because we're not having too much time, since quantum computation is not the only focus of this lecture. So I'd like only to recommend read a little bit about complexity theory if you really want to understand quantum computation in detail. So the strategy that we're going to do is more, we come from a point of view, so in the last 2 weeks we understood now the formalism of quantum mechanics in a more informational theoretic description, and we're now going to use this and we go into quantum computation. So I'd like to give you an insight into quantum computation based on a more approach from someone who's studying physics, right? And as I mentioned, the first point that we're going to discuss is our information carrier. So if we're speaking about computation, then you know from classical computation that all these tasks are performed by simply performing gate operations on bits. So classically a bit is either 1 or 0. And we are now defining our quantum mechanical counterpart, which is the qubit. Qubit is a 2-level system, and instead of being either 1 or 0, it can be now also in a coherent superposition. Okay? So yes, 2.1 qubit. So we define a qubit as a quantum mechanical 2-level system. So it's a 2-level quantum system. Described described by the Hilbert space H is 2, and then we call the basis states 0 and 1, right? We call them the computational basis states. So the orthonormal basis states 0 and 1, they are called the computational basis states. choice of these states is arbitrary, right? We can define these states as we wish. However, this must be an ON basis. So the choice of these states is arbitrary. So by this I mean, for example, if you take a photon, you can, for example, say the horizontal polarization is 1 and vertical is 0, or you can go into another basis and say the diagonal polarization is 1 and the anti-diagonal 0. And this is what I mean by the choice of these states is arbitrary. However, here we simply say, okay, there is such an ON basis, and we call this ON basis then the computational basis set. So some remarks here. Then first is that a pure state or a pure single qubit state is described by the state vector so this we know. It has two coefficients A and B. Where the modular square must sum to 1 since we consider normalized states. So secondly, I'd like to mention here that in this chapter, meaning in our discussion of quantum computation, we mainly work with pure states. So in this chapter, we mainly consider pure states. And to be, in order that we also can discuss density operators, so mixed states, we can now also introduce a density operator. As I mentioned, we are not going to use this often, but a possibly mixed single qubit state is described by the density operator rho, which is element of the density operators of our Hilbert space C2. Okay. With this, we have now a formal definition of what a qubit is. And our next aim is to see, okay, what operations can I do on these qubits? And for this, I first would like to define the Pauli matrices, since these Pauli matrices are very important when we speak about gate sets. That's chapter 2.1.1, Pauli matrices. So it's definition 2.2. Pauli matrices are defined as, I guess you all remember them. It's sigma 1, which we also call X, which is 01, 10. Then we have sigma 2, which we also call Y, which is O minus I, O. And then we have sigma 3, which is also called Z. It's 1, O, O minus 1. This is equation 2.2. Okay, so some remarks here. So this is now simply being a definition of these Pauli matrices to remember them. The first remark is a property. This is useful. So the property is that Pauli matrices, they satisfy that if you multiply sigma j with sigma k, you have delta jk times identity plus sum over L equals 1 to 3 of epsilon jkl sigma L. Okay, what is this epsilon? First, this is equation 2.3. So with delta jk is the Kronecker delta. And epsilon jkl is the Levi-Civita symbol. And okay, and this holds. So this holds for all jk in the set of indices. So what it tells us, okay, that if I have j equals k, then I have the identity because this one vanishes. So for two indices which are the same, the Levi-Civita symbol vanishes. So if j is equal to k, then we have the identity. So they're square to the identity, the Pauli matrices. And if they're unequal, then this vanishes, and this on here there only remains one non-vanishing summand, meaning that if you multiply two different Pauli matrices, you get the third one, and then there's a sign which depends on how you multiply them. Okay, then the second remark is an important remark, and this is actually the reason why we do need these Pauli matrices.
Is there a missing I because if we multiply x and z, that integer?
There's no I missing, no. If you multiply x and z, so then this is a real, and then this, why is there an I missing? It can be, sorry. X, Y, Z minus. Flip this. Minus 1. Yes, there should be an I missing. Okay, sorry, it's wrong in my notes. Okay. Yeah, I think you're right, and there must be an I missing. Okay. Good, let's continue. I'm gonna check this. I'll let you know next time. So let me say again. Okay, the reason why we define this already here at this place is these Pauli matrices are important because together with the identity, they span a basis of the real vector space of 2 by 2 Hermitian matrices. Okay. So let's write this down together. The Pauli matrices together with the identity, we say sigma naught is the identity. The Pauli matrix together with the identity constitute a basis of the real vector space hence V0, V1, V2 and V3 in R, as we will see in a second. So they constitute the basis of the real vector space of 2 by 2 Hermitian matrices. And what this means is that we can write any 2 by 2 Hermitian matrix as a superposition of these 4 matrices, namely the Pauli matrices and the identity, with real coefficients. So this means that any 2 by 2 Hermitian matrix can be written as so any 2 by 2 Hermitian matrix, let's call this A, the matrix, can be written as A is equal a constant factor that's arbitrary, and then we have V0 times sigma naught plus V1 times sigma 1 plus V2 sigma 2 plus V3 sigma 3, which is 1/2 V0 identity plus a vector V times a vector sigma, which I explain in a second. So where V0, V1, V2 and V3 are real, then we have the vector V is V1, V2, V3, which is of course in R3, and the vector sigma is a vector which contains, so it is a vector with the Pauli matrices, sigma 1, sigma 2, sigma 3. Okay, meaning that any Hermitian matrix can be written in this form with V0 real and this V here being an element of R3. So remark 3 is if additionally A, so the matrix A, is positive and has unit trace, And then V naught is equal to 1. And this vector V is bounded, so the modulus of this vector is bounded by 1. And hence, we can write down A as A is equal to 1/2 times identity plus a vector V times sigma. And this means that any density operator describing a state of a single qubit can be written in this form. So now you see the reason why these Pauli matrices are so important, because any state of a qubit can be expressed with the help of these Pauli matrices. And the only variables that are left over is this three-dimensional real vector V. And then the last remark is just 2.7, 2.6, okay. So the last remark is now specifying this vector, the properties of this real vector in case of pure states. Namely, in the case of pure states, this has a length 1, so it's a unit vector. So if rho describes a pure state, then actually it's if and only if. So let me write this. If and only if rho describes a pure state, then the modulus of V is equal to 1. So with this, we now found a nice way how to express the density operator of a single qubit state. And we can simply express this via a three-dimensional real vector. Well, and we know how to illustrate a three-dimensional real vector, right? So we can use simply three-dimensional space to illustrate such a vector. And I forgot to say that all these statements that we've done so far, you can easily prove them, and possibly you prove some of them on the next exercise sheet. Okay, so all these proofs are not too complicated, and I think some of them you will calculate by your own, and you can also, of course, calculate all the other proofs by your own. So with this, we now, let me repeat this again, we now say that a density operator of a single qubit can be written in this form, and it is specified simply by this three-dimensional vector. And this can now be illustrated, and it's illustrated on the unit sphere, which is usually called the Bloch sphere. So this is our next subsection. So by equation, this is 2.6, this is also 2.6, okay. So by equation 2.6, so we can now illustrate such state. Let me now try to do so. Okay. So we have here Ex, Ey, and Ez. Then make a sphere. Now let me highlight some points here. So first, an arbitrary state. So it's a pure state, psi. We know that pure state lives on the unit sphere. This is what our remark 4 tells us. Okay, so any pure state lives on the unit sphere. And let me now introduce spherical coordinates. So we have here then the angle theta and here the angle phi. And then let me also mark that we associate here this state with 0. I use another color. So we have here 0, here 1, then here we have 1 over square root of 2, 0 plus 1. Here we have 1 over square root of 2, 0 plus I1. Then here we have 1 over square root of 2, 0 minus 1. And here 1 over square root of 2, 0 minus I1. And you see that in red I introduced now the spherical coordinates, so we can write down our three-dimensional real vector v in spherical coordinates. So v is equal to the length of the vector, and then we have sinus theta, cosinus phi, sinus theta, sinus phi, and cosinus theta. Where v small equal 1 and 0, so theta runs between 0 and pi, and phi between 0 and 2 pi. Okay, and as we know from this remark 4, that pure states lie on the surface of the Bloch sphere. Okay, and how can it be written? So they can be written in this form that we have cosinus theta half as the coefficient in front of our computational basis state 0, and then a relative phase e to I phi and the sinus of theta half. And you can really see this here in this representation. For example, set theta equals to 0, and then the right term vanishes and we have psi is equal to 0. Okay, this is exactly here. If we have theta equals 0, we're there. And if we increase theta, the more we increase it, the more we go from the state 0 to the state 1. And then the relative phase between 0 and 1 is on this xy plane. So it's the phase phi, which defines where we are on this xy plane. Okay, and you can see that in the very beginning we also said again that these coefficients, the modulus of these coefficients must square to 1. And this is what you can see here. So if you have cosinus squared plus this modulus squared is the sinus squared, and this gives 1. So that's how we write down pure states, pure single qubit states. Okay, so let me calculate this for a second. So by comparing with equation, I think it was 2.1, we see that A is equal to, so if we write down psi as A times 0 plus B times 1, then we get equation 2.8 by setting this coefficient A as e to the I gamma cosinus of theta half, and B as e to the I times gamma plus phi sinus of theta half. And this phase e to the I gamma gives then a global phase and cancels out. So if we set these coefficients and we plug them in here, then we get back 2.8. Okay, and I think this is the right time to do a break, a bit early today, but it fits better into what's coming next. So let us do a break and meet in 10 minutes. In the first session today, we described qubits, and in particular there we have seen that qubits can be illustrated on the Bloch sphere, on the unit sphere, and they can, on this sphere, be characterized by a single three-dimensional vector. So this is, in a sense, what we learned before the break. And as I already mentioned before the break, the aim is to perform operations on many qubits, right? So consider a register of many qubits and then an operation there which performs a task. This is what we aim for in quantum computation. And we are now heading towards describing these transformations. In particular, what we want to see is, or what we're going to study is, a decomposition of many qubit operations into a finite set of single and two qubit gate operations. Okay? And with this, I'd now like to set the starting point with discussing single qubit operations first. So this brings me now to the chapter 2.2, which is quantum gates. And first we discuss single qubit gates. So imagine you have a single qubit, so simply a two-level system, and you're performing an operation there, and we've seen that we can imagine this now on the Bloch sphere. And suppose you perform an operation and possibly one more and one more, and it is actually intuitive that these operations must preserve the norm of these states. Okay? So they must preserve the norm of the states, and an operation which preserves the norm of a state is a unitary operation, meaning that any gate operation must be unitary. Okay? So any gate operation on qubits, so on single qubit and on a set of qubits, so I write on qubits, must be unitary. Since the norm of the state must be preserved. Okay, this is the ideal case, right? And we're starting with the ideal case. And more general quantum operations is what we describe if we later on study quantum information theory in more detail. There we're going to study in detail what kind of quantum operations are there and what kind of effect do they have. Okay, but for ideal operations, they must preserve the norm. Okay, then we are not running into trouble. That's what we do want so far. Then, okay, now let's come back to single qubit on the Bloch sphere. If it's not preserving if it's preserving the norm, such an operation, and suppose you're given a pure state and it must preserve the norms, meaning it must preserve the fact that it lies on the unit sphere, and then a gate operation on such a single qubit is nothing else than a rotation on this Bloch sphere, right? Because the operation must be such that it remains on the sphere of the Bloch sphere, so on the sphere itself. If it preserves the norm. If it would not preserve the norm, then the state would go inside the sphere, right? Because then it would get mixed and get inside. Or it would get outside if you're having not normalized states. But we want an operation to preserve the norm, and this means it must lie on the sphere, on the unit circle. And since all the pure states of qubits live on the sphere, so on the outside of the sphere, we can describe a unitary operations by simply a rotation on the surface of the sphere. So single qubit gates correspond to a rotation of on the Bloch sphere. These rotations, they can be generated okay, surprisingly, they can be generated by the Pauli operators. And namely, it's such that a rotation around the angle theta, by the angle, sorry, a rotation by the angle theta around the axis or around a unit vector. Let's call this n. So I give it a head saying it's a unit vector. It's mediated by the unitary, and we call this R, so it's a rotation by the angle theta around a unit vector n, and it's e to the minus I theta half, and then we have n multiplied with this vector sigma. This equation 2.10, where n sigma is equal to n1 sigma 1 plus, no, I called it x, I think. Okay, let's call this 1 and 2, 3. I like this notation better. 1, 2, 3 with n1 sigma 1 plus n2 sigma 2 plus n3 sigma 3. Okay, so this describes a rotation. But in order now to describe any unitary operation, we also have to add a general phase here. Okay. So accordingly, any unitary operation or the transformation of a single qubit can be written as a phase e to the I alpha, and then a rotation around some unit vector n by the angle theta. So here alpha and theta are angles, and n is a unit vector. So with this, we found a way how any single qubit unitary can be written, right? But most probably this is not the most convenient form to write it down. So this means that in a second I will show you also other ways how we can write down unitaries. And these other decompositions that I show you, these ones we're gonna need further if we describe gates between multiple qubits, so control gates. Okay, this is what we're gonna do in a bit. But well, this is a way how we can write them down in general, simply a rotation and a phase operation e to the I alpha. And let me now state a few important gates that we're gonna see every now and then. So besides the Pauli X, Y, and Z gates, we often use the following important single qubit gates. The first one is called the T-gate, or sometimes also called the pi/8 gate. Okay, and it has the form T is equal to e to the minus I, no, it's e to the minus, yes, I pi/8, and then e to the, oh, here's a plus, e to the I pi/8, e to the minus I pi/8, 0, 0, e to the I pi/8, which gives 1, 0, 0, e to the I pi/4. So the reason why it's called pi/8 gate is because you can write it down in this way. So it has an historical reason. The next thing is the phase gate. So I call it S, which is T squared, which is 1, 0, 0, and I. And then we need the phase shift gate. Which we call P phi. So it's a phase shift because if the qubit is 1, you multiply it with the phase e to the I phi. So you see that the T-gate and the phase gate are special instances of the phase shift gate, right? But they are so important that I'm going to state them separately. And then the last one is the Hadamard gate. You can write this down as 1 over square root of 2x plus z, which is 1 over square root of 2, 1, 1, 1, minus 1. Or you can write this down as e to the I pi/2, and then a rotation about the axis n with angle pi. Where this unit vector n is equal to 1 over square root of 2, 1, 0, 1. Okay, just that you see that, okay, this is how we write it down in this form. And the Hadamard gate is a very important gate. And we will see this very, very often. So this now brings me to some remarks. And as I already mentioned, we're going to need some decompositions of unitaries later on. The first thing is the first decomposition is as follows. So suppose we have some given two non-parallel given unit vectors. So given two non-parallel unit vectors m and n, any single qubit unitary can be written as u is equal to e to the I alpha, so the phase operation, and then with a rotation about n by the angle beta, and then a rotation about m by the angle gamma, and a rotation n about gamma delta. This is equation 2.16. So where alpha, beta, gamma, and delta are angles. So they are real numbers. So remember here, we stated that any unitary can be written in this form. That means that we possibly have to rotate, so we have to rotate about a specific unit vector. And this one here says that given any two unit vectors, we can perform any unitary in this way, now with 4 different angles. Okay. Now the next decomposition of a unitary is an interesting decomposition that we're going to use, I think, the next time. So on Wednesday, on Thursday, sorry. And it's as follows. It's our remark 2. If U is a single qubit unitary, then there exist single qubit unitaries A, B, and C, such that if I multiply them, A times B times C, I get the identity. And that U can be written as e to the I alpha. And then we have A times the Pauli X gate, B X gate C. Question 217. And this. Okay, then next one is more a remark on language. It's then the Pauli X gate. It's also known as the controlled or controlled CNOT-gate, or the quantum CNOT-gate. Sorry, not the quantum CNOT-gate. Oh. it's not the controlled NOT gate. Oh, not slow. It's not the controlled gate, sorry. I was already too far in my head. It's the NOT gate. So the Pauli X gate is also called NOT gate. Why? Since if x acts on 1, you get if x acts on 0, you get 1, and if x acts on 1, you get 0. Okay, then. Fourth remark is we usually illustrate gate operations by quantum circuit diagrams. So, quantum gates are usually illustrated by quantum circuit diagrams. And for the single qubit gates that we described so far, they are as follows. So for the above, first let's say, okay, what is a quantum circuit diagram? Quantum gates are usually illustrated by quantum circuit diagrams where first this time runs from left to right, and qubits are illustrated by wires. And the above single qubit gates are illustrated as follows. So we had here the T gate, the phase gate, and the phase shift gate. So it's the T gate. We have a circuit for one single qubit, and the gate is illustrated by a box, so it's T. And similarly for phase gate, so we have again a circuit, a wire for a single qubit, then a box for the phase gate, then S, okay, and so on. Similar for the other gates. And the Pauli, for example, the Pauli X, it's also such. So Pauli X gate also acts on a single qubit. Qubit is a wire, the gate is the box, and similar for Y and Z. So these quantum circuit diagrams, they allow us to get an intuition what's happening there, to illustrate, so to say, these operations. And they become particularly important if we have a lot of operations and also operations between different qubits, which we're going to discuss next. But I also would like to warn you at this point that at some points these circuit diagrams can become very complicated, such that you don't have an intuition what's actually going on at these diagrams, because they're simply too complicated to really understand them. And if it is such that you're not having intuition what's going on there, then I guess that the best thing is to sit down and calculate what's going on. Okay. Often there's some combinations of gates that you can understand if you heard them before, but sometimes you're confronted with a huge circuit diagram that you may want to understand, and then it's best, okay, that you calculated the parts and then try to understand what's going on. And the next thing is now, we've now discussed single qubit gates. And of course, with single qubit gates, you can only do operations on a single qubit, and this is not enough because it's simply a rotation in the Bloch sphere. And we now want to see, okay, what kind of operations or which particular operations are interesting if I have two qubits. Okay. And the most important, I'd say, and also most prominent two-qubit operation is the so-called CNOT-gate. That's chapter 2.2. So one of the most prominent and most important two-qubit gates is the controlled NOT or sometimes simply called the CNOT quantum gate. It has the following matrix representation. So it's C0. Since it is a two-qubit gate, the matrix representation must be a 4x4 matrix. Okay? Because we have, as a dimension of the two-qubit Hilbert space is 2 times 2, so it's 4. And the C0 representation is as follows. So we have 1, 0, 0, 0, 0, 1, 0, 0, 1. And the circuit diagram is as follows. So, as you can see here, by the circuit, we now have two wires, meaning we have two qubits. So there's a qubit associated to this wire and a qubit associated to this wire. And then the CNOT gate says, okay, the first qubit, which is usually called the control qubit, and the second is usually called the target qubit. And it's such that, okay, if the control qubit is 1, then the target qubit is flipped. Okay, so this here, this small dot means a control on the first qubit, and what I do is I flip the target qubit. Okay, and this symbol here is meaning nothing else than performing a Pauli X operation, so a NOT operation. And that's where the name comes from. It's a controlled NOT operation. And in the matrix representation, you can always see it. So this state, here the state corresponds to the state 0, 0. Here we have 0, 1. This is 1, 0 and 1, 1. Similar here, we have 0, 0, 0, 1, 1, 0 and 1, 1. And we see that, okay, in this subspace here, where the first qubit is 0, nothing happens, the identity. Okay? The reason is that only if the first qubit is 1, then something happens on the second qubit. And this is what described in this subspace. So here this subspace corresponds to the first qubit being in 1. And what happens is a flip of the second qubit. That's why we have here the representation of the Pauli X gate, so the NOT-gate. We flip it. So first qubit is usually called control qubit. And the second target qubit. So then there's one important property, namely the CNOT-gate is unitary, of course, and it is self-inverse. Since if I square the CNOT, I get the identity. So how does it act on the computational basic states? I already discussed it here. So it acts on the computational basis states as CNOT acting on A tensor. I'm not writing the tensor product here, but A tensor B is equal to A tensor B, and then we have the summation modulo 2 with A. So where this plus means the addition modulo 2. Let me now briefly state for completeness how the CNOT-gate acts on our basis states. So I'm now writing out this for all 4 different basis states, computational basis states. So we have, in particular, so if CNOT acts on 1, 1, let's start with 0, 0. Well, then our first, which is the control qubit, is 0. And if it is 0, then nothing happens, right? So nothing happens on the second, so it remains the same. Then if we have 0, 1, again, the control qubit is 0, so nothing happens on the second. It remains the same state. C0 acts on 1, 0. Well, now the control qubit is 1. And as the name says, it controls now a NOT gate on the second qubit. So the second qubit is flipped, and we get 1, 1. And C0 acting on 1, 1. Same thing, now our control qubit is 1. And since it is 1, it controls now the execution of a NOT gate on the second qubit, and we get out 1, 0. So this is okay, some remarks. First remark is the matrix representation that we used. Okay, I actually here already used the matrix representation, and let me now specify this in detail. So we use for the computational basis states we use the matrix representation so we write 0, 0. You know this, we also write this in this form, or write this as simply 0. This is our matrix representation. And then 0, 1. Then we have 1, 0. Sometimes we also write this then as 2, sorry. And 1, 1. And similar for more qubits. Okay, with this I'd like to stop here for today. And next time we're gonna write down some more remarks for our CNOT-gate. And then with this we continue to controlled unitary operations and then to controls on multiple qubits. So gonna see you next time on Thursday.